Testing. Okay, welcome to another Ginger Mathematician video where we're going to go through a past IB high-level applications past paper from June 2021, and this is time zone 1. This is a 2-hour paper. Okay, it's about 110 marks in total, and we're going to be using that formula booklet to help us and the GDC all the way through. Let's get started. So, question 1, we have George going fishing. From experience, he knows that the mean number of fish he catches per hour is 1.1. And as soon as you have a rate of some kind, you need to be thinking anyway a Poisson distribution. Now, with a very straightforward question like number 1, it will tell us actually here that assume that the number of fish he catches can be modelled by a Poisson distribution. So we're kind of told that already, but you need to be looking out for per hour or per minute or per second, generally indicates a Poisson distribution to use. Now, on a day in which George spends 8 hours fishing, we want to find the probability he will catch more than 9 fish. And notice I'm underlining the key vocabulary of the question here. So he catches 1.1 per hour and he's going to fish for 8 hours. So on average, he's going to catch 1.1 times 8, which is equal to 8.8 fish. So that's going to be our rate over the 8 hours. So that's what we're looking for. Remember, with a Poisson distribution, we're going to be looking for that lambda. So in this case, lambda is going to be equal to 8.8. Now we look at the other parts of the question, and we want the probability they will catch more than 9 fish. So x, our variable, is going to be greater than 9. And remember, greater than 9 basically means we want the probability of x greater than or equal to 10. Because when we use our calculator, it's going to include the 10 and then go from there. So now we're going to go over to my GDC and pop it in the calculator and show you how to do it. Okay, so make sure you've got your graphical calculator ready for this test. For here, we're going to go to Menu, we're going to go to Probability, we're going to go to Distributions. You can also go via Statistics as well. And we're going to scroll all the way down. It's right at the bottom here with our calculator, right down to Poisson distribution. Notice there's so many things that this calculator can do. Now, because we're looking for a range of values, not a specific value, we're going to use Poisson CDF. So we click on that. Now, our rate was 8.8. Our lower bound is going to be 10. Because we want 10 or greater, i.e. greater than 9. And now the upper bound, we don't want to put a really huge number, but we want to put a reasonably large number. So I'm going to put in here 500. Make sure this is a reasonably large number, and press the equals button, and then we'll get the answer of 0.38626. So let's write that over on my PowerPoint. Okay, so the way I would actually show this, in terms of showing the examiner what I'm doing here, I'm going to go to Poisson CDF. I'm going to write the rate down, so 8.8. I'm going to write the lower bound, which is 10. Now I've just chosen 500 as a big number to make sure I get the most accurate answer possible. And I'm going to get 0.38626 ... And then, of course, that is equal to 0.38623 SF for our 4 marks. So, nice straightforward question to start with. Make sure you know where the Poisson CDF function is on your calculator and how to put in the correct values. And you can see the mark scheme here. So, 1 mark for setting up your Poisson distribution of 8.8. Realizing, of course, you want x is greater than or equal to 10. Giving the method mark there. And then finally calculating that and rounding, giving us up to the 4 marks that we need. Okay, question 2 is a nice Voronoi diagram. So we've got identical cellular phone towers, T1, T2 and T3, and T4 is in the shaded region down here somewhere, and the dashed lines in the diagram represent the edges of the Voronoi diagram. So this is a topic that's been added to both applications, stand level and high level, so you really need to get a hang on this particular topic. Now, Tim stands inside the shaded region. Explain why Tim will receive the strongest signal from T4. And the reason for this, that any point in that shaded area, so any point in the shaded area, is closest to that tower. So it's closest to T. So whether I am standing here, standing there, the whole point of a Voronoi diagram is wherever I am within this cell, I'm closest then to T4. That's the definition of a Voronoi cell. And now we're told that T2 has coordinates -9, 5, and the edge connecting vertices A and B has the equation y equals 3. So this line here is equal to y equals 3, so it's a horizontal line, and we want to work out the coordinates of tower T4. Well, T2 here is equal to minus 9, 5. This is equal to, well, this is y equals 3, so 0, 3. So what we want to do is find the tower here. So if I draw roughly where it's going to be, this is going to be T4. So notice we want to look for the gap between the y coordinates, 5 and 3. So if I do this in a slightly different colour, so do this in blue, the gap here is going to be equal to 2. So in order for this to be a perpendicular bisector, this also needs to be a gap of 2 as well. Well, let's think about what that's going to make our coordinate. Well, notice the x-coordinate hasn't changed here, so that's going to stay as minus 9. Well, from 5 to 3 is going to be 2, so we want to go 3 and then 2 more down, that's going to be equal to 1. So our coordinate is going to be minus 9, 1. And tower T1 has coordinates minus 13, 3, so let's write that in. And we want to find the gradient of the edge of the Voronoi diagram between towers T1 and T2. So what that's saying in normal English is if I draw over that line that they mention, we want to find the gradient of this line, the steepness of this particular line. Now remember, this line is a perpendicular bisector of T1 and T2. So what does that mean in order to work this out? Let me get out the black pen here. If we connect up T1 and T2 like so, what this means is this green line meets that line at a right angle. And we can exploit that fact a bit later on. The first thing we need to do is work out the gradient of that black line I've drawn in here. So the gradient, black line, and this is where we use our formula sheet. So this formula I'm going to give you is directly on the formula sheet. I'm just taking it straight from there. So we have y2 minus y1 over x2 minus x1. Now, what do these things actually mean? Well, let's label our coordinates. So I'm going to call this first number minus 13x1, the 3y1, the minus 9x2, and the 5y2. And all we have to do now is just put the numbers into the formula. So we have y2 as 5 minus, we have y1 as 3, so we get 5 minus 3 on the top. And on the bottom we have x2, so that's going to be minus 9, and then we're going to have minus, and x1 is minus 13, minus 13. Of course you can use a calculator at this point. Well, 5 minus 3, however, is going to be 2. Minus 9 plus 13, 2 minuses make a plus, that's going to get equal to 4. And of course 2 quarters is the same as 1 over 2. So that's the gradient of the black line. This is equal to minus 2. And what we can do now to actually work out the gradient of the green line, which is what we want for the question, is we're looking for the negative reciprocal. Now what does that actually mean? Well, what we do is we take this fraction, not flaction, a fraction, we put 2 over 1, so I'm just flipping that fraction, and I just put a minus in front. Okay, so that's what I mean by negative reciprocal, and of course this is just equal to minus 2. So the answer to this question here, m equal to minus 2, the gradient of the line. Now some questions, more advanced questions, would ask you actually to work out the equation of the line using the midpoint, and maybe doing something a bit with that as well. But certainly for a straightforward Voronoi question, these are the typical skills that you are expected to know. Okay, and you can see the mark scheme here and see everything that I did here. I even used the phrase negative reciprocal when I explain this, but you can see exactly where you pick up. Okay, question 3. So we have Charlie and Daniela, and they each begin a fitness program. Good for them. So on day 1, they both ran 500 meters. And each subsequent day, so the day after, Charlie ran 100 meters more than the previous day, whereas Daniela increased her distance by 2% on the distance ran on the previous day. And we need to calculate how far Charlie and Daniela run on day 20 of the program. So if we take a part 1, so we're going to focus on Charlie first of all. So the sequence would go here, so we've got 500, and then she runs 100 meters more the next day, so that's going to be 600, and then 700, and so on. And what we need to do here is work out how far on day 20. So the way I'm going to do this is work out the nth term. So how do I do that? Well, I look at the difference each time, which is 100. So it's going up by 100 each time. So our nth term is going to be 100n. And then what do we do to 100 to get to 500? Well, we add on 400. Okay, like so. And this allows us then to work out day 20 of the program. So we're going to work out U20. And the way we do that is replace the n here with 20. So we get 100 lots of 20 plus 400. Well, 100 times 20 is 2,000. 2,000 plus 400 is 2,400. Okay, we're going to use the formula from the formula sheet a bit later on for part B. Okay, so into part 2. So now we're looking at Daniela. So she's increasing her distance by 2% each time. So if we have 500, well, we can actually work this out manually if you wanted to, but extra 2%, that would be an extra 10 meters. So this would be 510, and so on like this. What I'm doing to actually work this out is I'm multiplying by an increase of 2%. Remember, an increase of 2%, well, 100% plus 2% is equal to 102%, and this as a decimal is equal to 1.02. So essentially, to work out each term in the sequence, we'll multiply by 1.02 each time. So we can work out the nth term from this. So the nth term, this comes directly from the formula sheet, is U1, which is going to be our first term, 500, multiplied by the multiplier, which is 1.02, and then to the power of n minus 1. Again, this comes directly from the formula sheet. I'm going to go over there and show you where these formulae are. Okay, so you can see the two formulae here. So I'm using this formula here, so the U1 r to the power of n minus 1. And I used a slightly different way to work it out, but you can use this formula here as well, U1 plus n minus 1d. So these are the two formulae you need to know from your formula sheet in order to successfully do this question. Okay, and back to the question. So what we need to do now is work out U20. Change to red. Okay, that's a bit random. So we're going to change to U20. So that's going to be 500 multiplied by 1.02. And wherever we see an n, we're going to put a 20. So 20 minus 1 is 19. And this is something we can't do on our head, so we're going to go over to my GDC and work it out. So we type in 500 multiplied, open bracket, 1.02, close bracket. This button here is very useful, gives you to the power of. We type in 19, and then we get our answer of 728.4. So we're just going to pop that over now. Okay, so 728.4 meters. Again, if you want to do that to 3SF, it's going to be 728 meters, like so. Okay, and on to question B. So on day N of the fitness programs, Daniela runs more than Charlie for the first time. And now we need to find the value of N, so when that happens. So this is when we're going to use the two formulae that we just saw on the previous page, on the Revision Village formula sheet. So what we need to do here is write an expression for both in terms of n. So if I take the formula from the formula sheet, remember this was the formula for an arithmetic series, an arithmetic sequence. So if we put the values in of d and u1, well, u1 is equal to 500. Okay, n this time we don't know. And d is going to be equal to 100 because it keeps running 100 extra. So that's going to be our nth term. So this one is for Charlie. And then for Daniela, we have an nth term of 500, 1.02 to the power of n minus 1. So just a reminder of what we did earlier. And we want to work out when this one, the bottom one, is bigger than the top one. So essentially we're looking to work out when 500, 1.02 to the power of n minus 1 is greater than 500 plus n minus 1 times 100. And you look at this on the surface and go, how do I solve such an equation like this? I've never been taught this. Well, this is where our graphical calculator comes in, and we're going to graph both and find the intersection point. So we're going over to the graph page. So we're going to go and create a new document, and we're going to go to graph, and we're going to put in the first function. So 500 multiplied by 1.02, close bracket. Now remember, because we're using our variable as x, we need to put x here as well, x minus 1. And notice we don't see the graph anywhere, but don't worry, we'll come back to that in a moment. We press the tab button, And now we're going to type in the other function. So 500 plus, open brackets, x minus 1. Remember, x is our variable, not n here, times 100. Again, we see something kind of random, and you go, okay, something's gone wrong. But don't worry, all we have to do is go to Menu, we go to Window Zoom, and we use the wonderful button known as Zoom Fit down here. Now, if we do that, you'll now notice that actually it will automatically move around the axes, so we can actually find something that's useful for us. So we've got our two functions here. So 500 times 1.02 power of x minus 1 didn't disappear. And we have 500 plus, open brackets, x minus 1 times 100. And all we need to do here is find the intersection point. However, this is not the correct answer. Well, in fact, it was the correct answer. So this is when they started at 500 meters. So we need to find the next solution. So we need to find when this blue line here, or blue function here, is actually bigger than the red function. And you're saying, well, actually, it doesn't look like it's ever going to happen because the red function is going off in this direction. Well, this is where we can actually, if we drag along this function, we can actually see it's going to. Then we might need the help here of zoom out. We're looking for the next time that the two functions cross. And you'll notice if you zoom out far enough, there is a situation where they cross again up here. So this is what we're looking for. So this red line here, this is Charlie, so running faster than Daniela, running faster than Daniela, running faster, and then as soon as we get to this point, this is when Daniela runs faster than Charlie. So we need to find this intersection point here. We do exactly the same process as before, analyze graph, intersection, we click before, we click after, and then we get our value of 184.2. So we're going to go back to my PowerPoint and write that in. Okay, so we've written in the value of 184.2, but remember, we're looking for when Daniela runs more than Charlie for the first time. So in this case, we actually need to round upwards. So it's going to be the 185th day when Daniela runs faster. Okay, so even though normally we wouldn't round up to 185, because it goes beyond the 184th day, that faster run is going to be on the 185th day. So when Daniela runs faster. So you can have a look at the mark scheme here as well, and you can see where we picked up all those really important method marks. And on to question 4. So Professor Way observed that students have difficulty remembering the information presented in his lectures. That's certainly the same for my lessons as well. And he modelled the percentage of information retained R by this function R, t equals 100 e to the power of minus pt, where t is greater than 0 because it's time, and t is the number of days after the lecture. And he found that one day after a lecture, students had forgotten 50% of the information presented. Now, using this information, we're going to find the value of p. Okay, so we're going to pop this in. So when t is equal to 1, then students have forgotten 50% of the information. So r is going to equal 50. So we substitute those values into our function here. So we get 50 is equal to 100 e to the power of minus p. Remember, t is 1, so 1 times p is just p. And so we need to find out what this value here is. Now, there's a couple of ways you can certainly do this. I'm going to use a graphical approach to find this. Okay, so back to my graph function. This time I'm going to type in 100, and I'm going to use the E button down here. Okay, and remember we have to use X whenever we're using a variable. So we get this function here. So 100 e to the power of minus x. Now remember we wanted this function to equal 50. So we go tab and 50. Of course, we're not going to see the line because we'll need to actually drag upwards until we can actually find 50. So there's our 50 point there. At this point, we find our intersection point, analyze graph, intersection. You could have zoomed out as well. And then we get our answer of 0.693 to 3 significant figures. So I'm going to pop that in over here. So therefore, P is equal to 0.693 to 3 significant figures. And if you wanted to, you could also draw a sketch of what we just did there. So you've got the function, and then we've just drawn a line across at 50 and found that intersection point. Okay, so if you ever get stuck with solving any equation, we could have done that algebraically for sure, then you can always use your graphing function, put the two functions in, find the intersection point, and then you'll have the correct answer. And now we're going to use this model to find the percentage information retained by students 36 hours after Professor Wei's lecture. So we're going to put in some values here. We already know what P is now, so P is now equal to 0.693 ... because it goes on for a long time. And we're going to put in T, well, that's going to be equal to 36 hours. So remember 36 hours, that's going to be the same as 1.5 days. Yeah, 1.5 days. So you have to be a little bit careful. I'd like to be tricky on these questions. So if we put that in, we're then going to get R of 1.5 is equal to 100. E to the power of minus P, so minus 0.693 ... times 1.5. At this point, we're going to go over to my GDC and work out the answer. Okay, and if we put that into our calculator, you'll see we get the answer of 35.363. So we're going to pop that back in over here. So 35.363 ... Of course, to three significant figures, which is always what we round to, we get 35.4%, which is the answer that we're looking for. And based on this model, Professor Wei believes his students will always retain some information from his lecture. And we need to state a mathematical reason why Professor Wei might believe this. Well, remember that sketch that we did before. So just remind you what the function looks like. So an exponential decay model looks like this. But the key thing, we never actually touch the x-axis because there is an asymptote there on the x-axis. That means basically the function will never touch the x-axis. It'll get very, very close, but will never actually touch it. So the reason that Professor Wei might believe this is because there is a horizontal asymptote, that's the word we need to use, at the x-axis. And last of all, we need to write down the limitation of the domain of this model. So remember this word domain, that means the x values. So why this wouldn't be so appropriate. The first thing to consider, so if I just put in my x and y's here, notice that this model would go on forever and ever and ever. So if we go back to what t in this case is, it's a number of days after lecture. So it's not likely you're going to remember this 500 years after you've had the lecture. So the idea that humans don't live forever, yeah? The idea that this model goes forever, but of course human lifespan is limited. So there's many different answers to this as well. I think that's the most straightforward one. If we look at the mark scheme, you can say large values of t are not possible. This is very, very true. The idea that you start at 100%, which is also not very realistic as well. You can see the mark scheme here, so feel free to go through the mark scheme and see what we did. I took this also graphical approach just like the mark scheme did, but you could have solved this using natural logs as well for sure. Okay, I hope you're starting to like this series. If you want to check out my paper 3 video where I go through a specimen paper 3 question on statistics, then check out the video you see right in front of you.